Hello my friends and welcome back to the You Can Do TV channel. A convoy of trucks rumbles along shimmering roads, cutting through the African bush from Richards Bay on the Indian Ocean to a vast platinum mine in Polokwane. Here, a team of 5 mechanics and 2 assistants will spend the next few days assembling a colossal 500-ton hydraulic excavator. The assembly begins with the slewing ring, a crucial component of the excavator's structure. The surfaces are meticulously cleaned, dried, and cleared of any grease or oil. Adhesive is applied and evenly spread. A 120-ton crane then lifts the slewing ring onto the undercarriage, where the screws are initially tightened by hand to the engaging torque and subsequently with a hydraulic wrench to the prescribed torque. Next, the middle section of the undercarriage is connected to one of the 2 track carriers. The screws are precision tightened, and the middle section is jacked up using sturdy supports. This allows for the careful mounting of the second track carrier. The crane delicately lifts the 35-ton load into position beneath the undercarriage, demanding millimeter precision. Again, the screws are securely tightened with a hydraulic wrench, and a bulldozer assists in joining the tracks, each track pad weighing nearly a ton. Once the slewing ring gear is lubricated with heavy-duty grease and adhesive spread uniformly, a second 100-ton crane is brought in. Under the direction of a single marshal, the 2 cranes lift the superstructure's frame onto the undercarriage. A dowel pin aids in fixing the frame on the slewing ring, with screws tightened manually to the engaging torque and then hydraulically to the specified angle, each marked as it is secured. The boom cylinders are mounted on the frame, with pins sprayed with lubricant before insertion. Using 2 cranes, the 37-ton motor module is carefully placed onto the frame. Specialists use laser alignment to adjust the electric motor with incredible precision, to within 1/100th of a millimeter. The next step is to install the C module, which contains the built-in electric switchgear compartment, followed by the assembly of the 4 slew gearboxes. Before lifting the boom, the stick cylinders and hydraulic hoses are mounted. The boom, now weighing about 50 tons, is positioned with the assistance of the 2 cranes. A large wheel loader drives in the massive, lubricant-sprayed boom foot pin. A mobile platform facilitates work at greater heights, such as mounting the boom cylinders. One of the cranes then installs the 7.2-ton cooler module, bolted securely from the inside. The heaviest module, the 60-ton counterweight, is the last component requiring the use of the two cranes. It is lowered slowly onto the frame and bolted down using a torque multiplier. For safety, railings, bridges, and walkways are assembled around the superstructure. The remaining components, including a grease barrel, tool cabinet, and service crane, are then fitted, with the mobile platform once again proving essential for mounting the stick. Great care is taken when fitting the extra-large, soundproof cab. Over the next few days, the team installs the excavator's hydraulic and electric systems. Once the grease and hydraulic oil are filled in, electricians conduct final checks. The dramatic moment arrives as the motor is started up for the first time, monitored by the onboard control system. Meanwhile, the mine prepares for the deployment of the giant hydraulic excavator. A staggering 650,000 tons of rock await loading. But first, the bucket must be mounted. Once more, a wheel loader assists in driving in the pin. The bucket cylinders are installed while the cable drum is mounted and connected to the undercarriage. Now, the giant RH2200E excavator, equipped with its 25 cubic meter bottom dump bucket, is ready for action. It proceeds to its deployment location, showcasing its immense strength as it loosens tightly packed rock and begins loading 150-ton trucks. The RH2200E's high loading performance proves reliable even under the most extreme conditions. During the guest-free period, TUI Cruises undertook significant maintenance work on Mine Schiff 6, including a complex operation to replace a defective crankshaft in one of its 4 engines. Despite the failure of one crankshaft, there was no cause for alarm due to the ship's robust power system. 5 months prior, the new crankshaft, assembled from individual parts, was ordered. The replacement process involved careful coordination by the experts from Turbotechnic, who maneuvered the 12-ton steel component into the ship. Captain Jens Troja oversaw the operation, which was carried out at the pier while the ship remained operational. To avoid cutting into the ship's hull, a wooden model replicating the crankshaft's dimensions was initially used to ensure a precise fit. The actual crankshaft, measuring 7.5 meters in length, was then transported through the ship in stages, utilizing chain hoists and transport eyes welded into the deck. The old crankshaft was extracted and the new one installed by lifting the engine block, which itself required substantial effort to raise its 80-ton weight by 1.9 meters. The defective crankshaft was removed through a specially cut opening and transported to Deck 2, then off the ship using chain hoists. The new crankshaft was carefully moved along the same route and positioned next to the hydraulically lifted engine block. This intricate process, from removal to installation, took approximately 16 working hours. After positioning, the engine block was lowered, secured, and reassembled. Following the installation, the engine underwent a series of tests and trials to ensure proper operation. The 5-axis machining of an aerospace component, specifically titanium teal 6 volts 4, represents cutting-edge manufacturing capability. Utilizing the FT4000 with a swivel head, this process epitomizes precision and efficiency in aerospace engineering. Heller's HF Series 5-axis machining centers are integral to this advanced machining process. These centers excel in dynamic and productive operations, featuring a swiveling NC rotary table with AB kinematics and highly dynamic torque drives. The second generation of the HF series enhances productivity and precision with upgraded spindle units and the Heller Zero spindle system, minimizing lifecycle costs. Key features include universal machining capability with the 5th axis integrated into the workpiece, enabling complex tasks in a single setup. Options like the gantry drive in the Z-axis and mill turn functionality further enhance versatility, suitable for both series production and single-part manufacturing. The machines support fast chip-to-chip times and high axis speeds, crucial for maximizing productivity. Hermli AG, headquartered in Gosheim, a small community in the southwest of Germany, is renowned globally for manufacturing some of the finest CNC milling machines. The company's reputation for precision, innovation, and excellence is built on decades of experience, cutting-edge technology, and a commitment to quality. The creation of Hermli's machines starts with understanding the specific needs of their customers. This customer-centric approach ensures that every machine offers performance features that provide real competitive advantages. Hermli's development process involves rigorous basic research and virtual stress tests, employing tools like FEM simulation and modal analysis. These preliminary steps guarantee that even before the first physical component is produced, the design has been refined for optimal thermal, static, and dynamic behavior. Once the conceptual phase is complete, Hermli moves to prototyping and extensive testing. The prototypes undergo a series of trials in real production environments to ensure they meet the highest standards of efficiency and precision. This meticulous process ensures that every Hermli machine performs reliably and consistently. Hermli's commitment to precision extends to every aspect of manufacturing. The company uses advanced manufacturing concepts and a unique array of machinery to ensure each component meets stringent quality standards. This includes everything from the machine bed to the spindle, with each part undergoing careful assembly by experienced professionals. The assembly process at Hermli is characterized by a high degree of integration and efficiency. Components are produced in-house, ensuring tight control over quality and production timelines. This approach allows Hermli to respond quickly to customer needs and deliver machines just in time. Hermli also places a strong emphasis on user-friendliness and operating safety. Their machines are designed to be easy to use and maintain, which is crucial for maximizing productivity and minimizing downtime. Hermli's reach is global, with machines installed in production facilities around the world. The company supports its international customer base with a comprehensive range of services, including training programs, a service hotline, teleservice, predictive maintenance, and remote diagnostics. This ensures that Hermli machines operate at peak efficiency and any issues are addressed promptly. This section is about the installation and lifting of the 950-ton reactor by the LR 11350 crawler crane. The LR 11350 crawler crane stands at the forefront of heavy lifting technology, particularly in the crane class exceeding 1,000 tons, 1,200 ust. Renowned for its exceptional load capacities, this crane is designed to handle substantial weights across its entire operating range. With a maximum hoist height of 220 meters and a maximum radius of 164 meters, the LR 11350 is ideally suited for a wide array of demanding lifting tasks, including offshore handling, wind energy installations, nuclear power plant operations, and heavy industrial applications. One of the most notable features of the LR 11350 is its innovative design, which facilitates ease of transportation and rapid setup. Each component of the crane is engineered to be no wider than 3.50 meters, 11.5 feet, and no heavier than 45 tons, 99,200 pounds. This modular design ensures that the crane can be transported using conventional methods, significantly reducing logistical challenges and transportation costs. Once on site, the LR 11350 can be assembled more quickly than any other crane in its class, thanks to efficient assembly processes. This swift setup time is a crucial advantage in industries where operational efficiency and time savings are critical. The versatility of the LR 11350 is further enhanced by its wide range of boom systems, which can be configured to meet specific project requirements. The crane can be used with or without a derrick system, adapting to various operational needs. The power boom option, for example, increases the crane's lifting capacity, making it suitable for particularly heavy or complex lifts. Additionally, the crane's ballast system can be configured with a ballast trailer or suspended ballast, providing further flexibility and stability during operation. This adaptability allows the LR 11350 to handle a diverse array of lifting scenarios effectively. Safety and ease of operation are paramount in the design of the LR 11350. The crane is equipped with advanced safety features, including load monitoring systems, emergency stop mechanisms, and robust structural components designed to withstand extreme loads. These safety measures ensure reliable operation, protecting both the operators and the surrounding environment. The LR 11350 is also designed with user-friendliness in mind, featuring intuitive control systems that enable operators to manage complex lifting tasks with precision. The ergonomic design of the operator's cabin, coupled with advanced monitoring and control systems, provides a comfortable and efficient working environment, reducing operator fatigue and enhancing productivity. When preparing for the installation of the LR 11350, a thorough site assessment is essential. Evaluating ground conditions to ensure they can support the crane's weight and operational loads is crucial. Identifying and removing any potential obstructions will facilitate smooth crane operation. Logistical planning for the transportation of crane components to the site must be meticulously arranged to avoid delays. Once on site, The installation process involves several key steps: delivering all crane components, assembling the base and track components, installing the main boom and modular sections, configuring the power boom and ballast system if required, and conducting comprehensive safety checks to ensure all components are functioning correctly. Operational best practices are vital for the efficient and safe use of the LR 11350. Ensuring that all operators are adequately trained and familiar with the crane's controls and safety features is a fundamental step. Regular maintenance, including inspections of critical components and systems, should be part of a routine schedule to keep the crane in optimal working condition. Continuous load monitoring during operation is necessary to prevent overloading and ensure stability. Additionally, operators should be mindful of environmental conditions, such as wind speed and temperature, which can impact crane performance and safety. We're in Toyota's factory. Here we will learn about the Sora fuel cell bus production process. The production process starts with the design and development of the bus's body, which takes into account the high-capacity external power output device and the human-centric universal design and functions of the Sora. It includes the fabrication of the frame, assembly of the body panels, installation of windows and doors, and painting. The assembly process starts with the chassis, which is the foundation of the bus, followed by the installation of the drivetrain and suspension components. The body is then assembled, and various mechanical and electrical systems are integrated into the vehicle, including the fuel cell stack and the battery. The Toyota Fuel Cell System, TFCS, is then installed in the Sora during the FC bus-specific manufacturing process. The TFCS, which was developed for the Mirai fuel cell electric vehicle, provides high environmental performance with no CO2 emissions or substances of concern, society, emitted during operation. Toyota designed the Sora with a stereoscopic shape that differs significantly from conventional buses, with LED technology used for the front and rear lights, creating an instantly recognizable FC bus. The Sora is 10,525 mm long, 2,490 mm wide, and 3,350 mm tall, with a capacity of 79 passengers, including 22 seated, 56 standing, and 1 driver. The FC stack and drive motor deliver a maximum output of 114 kilowatts and 113 kilowatts, respectively, with a high-pressure hydrogen tank capacity of 600 liters. The Ford Motor Company Thailand Limited has recently installed a high-standard paint shop with the help of Dur AG, a leading global supplier of plant and machinery for the automotive industry. One of the notable features of the paint shop is the skid locking device and skid locking check, which ensures that the vehicle bodies are securely fixed in place during the painting process. This prevents any movement or vibration that could cause imperfections or defects in the paint finish. Another key component of the paint shop is the EcoPaint Row Dip pretreatment system, which uses a rotation dip process to thoroughly clean and prepare the vehicle bodies for painting. This ensures that the surface is free from any contaminants that could affect the adhesion of the paint. The next step in the process is the electrocoating stage, where an electric current is used to deposit a protective coating onto the surface of the vehicle body. This is followed by an onolite flow control system, which monitors and adjusts the pH levels of the coating bath to ensure consistent quality. To further ensure the quality of the paint finish, the paint shop is equipped with an e-coat inspection system that checks for any defects or inconsistencies in the coating. After the inspection, underbody sealing is applied to protect the undercarriage of the vehicle. The EcoBell 2 system uses a rotating bell cup that dispenses the base coat material in a fine mist, which is then applied to the surface of the car. This creates a more uniform and consistent spray pattern, which results in a smoother and more even paint finish. Finally, the vehicles are moved to the top coat oven, where the paint is cured at a precise temperature and for a specific length of time. This is followed by a top coat inspection to check for any imperfections or blemishes in the finish. The truck 6-cylinder crankshaft machining process utilizes Heller's flexible production systems, designed for the complete processing of crankshafts and camshafts. These systems can operate as standalone machines or as part of an integrated production line, providing a comprehensive solution for the automotive industry. The core processes involved include RFK for external and internal milling of crankshafts, DRZ for turning and grooving, MCC15 for milling, drilling, and tapping, and RFN for external milling of camshafts. The RFK external milling system is particularly suitable for the mass production of small to medium crankshafts. It offers flexibility and high productivity, handling concentric and eccentric bearing journals, side surfaces, outer diameters, and special contours, often in a single clamping. The cutting speed is generated by the tool, while the feed speed is provided by the workpiece. Externally toothed tools are used, which replicate the profile to be milled. Interpolation with NC axes produces the offset crank pins and/or concentric main bearings, and workpiece rotation is managed by a round axis at feed speed, while linear axes guide the milling units. The engagement motion can be a direct plunge or a spiral interpolation to machine the bearing diameter and side surfaces. The workpiece is clamped and supported by hydraulic chucks that synchronize electrically to hold the workpiece and absorb cutting forces. An NC programmable steady rest, positioned on a separate guideway below the milling slide, offers support without restricting movement. Multiple milling units allow simultaneous machining of bearing diameters and relief cuts, achieving high precision and eliminating the need for preliminary grinding. This system can handle various operations, including main and crank pins in a single clamping, side surfaces, and outer diameters of crank arms, relief cuts, and crank arm profiles. By integrating these processes, the RFK system provides an efficient and precise solution for crankshaft production, enhancing overall productivity and quality. The manufacturing of the new 5-axis machining center, the F6000, by Heller represents a significant milestone in the realm of precision engineering and advanced manufacturing. Presented for the first time at EMO 2023 to an international audience, the F6000 showcases Heller's dedication to cutting-edge technology and excellence in machining. Design and development. The F6000 is built from the ground up with a focus on flexible series production. This design philosophy ensures that the machine can handle a diverse array of workpieces, making it highly versatile. Dr. Manuel Gerst, the company's head of development, spearheaded the project, emphasizing consistent standardization and the integration of key components produced by the company. This approach guarantees the highest standards of quality and reliability, hallmark traits of machines. Key features and innovations. Among the standout features of the F6000 are its completely redesigned swivel heads and integrated motor spindles, both developed in-house by the company. These components are crucial for achieving the highest levels of precision, dynamics, and cutting performance in 5-axis machining. The machine's head kinematics allow for intricate and complex machining tasks, crucial for industries requiring high precision, such as aerospace and automotive sectors. The F6000 also incorporates the mill turn function, which is essential for combined milling and turning operations. This function is enabled by the high-torque DDT, direct drive turning, rotary table, which facilitates complete machining in one setup. This eliminates the need for reclamping workpieces on separate turning machines, thereby enhancing accuracy and significantly reducing cycle times. This capability is particularly beneficial for series production, where efficiency and precision are paramount. Automation and integration. Automation plays a central role in the F6000's design. The machine comes standard with a pallet changer, which is the first level of automation. Additionally, the Automation Ready option allows for seamless integration with the company's rotary pallet storage, RSP, and standardized linear magazine solutions. This modular approach to automation ensures that the F6000 can be easily adapted to meet the evolving needs of production environments, further enhancing its flexibility and efficiency. Ease of use and accessibility. Engineers have placed significant emphasis on the ease of operation and accessibility of the F6000. The machine features the Siemens Sinumeric 1 control system as standard, which includes a 24 inches touchscreen control unit designed for intuitive use. This system simplifies the setup and operation processes, making it more user-friendly. The increased access to the work area and the optional Setup Assist feature further enhance the usability, allowing operators to quickly and efficiently set up and adjust machining processes. The spindle line is a critical element in the factory's machining centers, playing a pivotal role in ensuring the precision and efficiency of the entire system. The spindle, often referred to as the heart of the machining center, is responsible for transferring all machining forces to the tool. Even the slightest inaccuracy in the spindle can significantly affect the performance of the entire system. Therefore, the factory places utmost importance on the precision manufacturing and assembly of its spindles. To meet the stringent demands for precision, the factory manufactures and assembles its spindles in a specially optimized spindle line. This facility operates under air-conditioned conditions to maintain consistent temperatures, which is crucial for achieving the highest quality standards. The manufacturing process begins with driverless transport systems that deliver spindle blanks from an automatic warehouse to the initial station. Here, the basic shape of the components is formed through soft machining processes. Following the initial shaping, the components are sent to the in-house hardening shop, This tempering process enhances the wear resistance of the parts, preparing them for the high demands of machining operations. Once hardened, the components return to the spindle line for further machining. At this stage, the components are refined to within a few micrometers of accuracy, ensuring their precision. During the manufacturing process, the workpieces are transported via a flexible flow line system, allowing for seamless movement between various stages. The components undergo final precision machining on cylindrical grinding machines, where both external and internal geometric properties are perfected. This step is crucial for ensuring the high precision required in spindles. Throughout the entire manufacturing process, meticulous documentation and real-time data transmission are maintained. Measurement data is continuously evaluated to monitor and control the process, ensuring that each component meets the stringent quality standards. High-precision measuring devices are employed to detect any deviations, even those under 1/1000th of a millimeter. Only parts that pass these rigorous quality checks proceed to the next stage. In the final steps of manufacturing, the spindles are deburred to remove any remaining imperfections and then packaged for storage. These components are carefully stored in the warehouse till they are needed for assembly. Assembly of the spindles occurs in a well-organized parts supermarket, where an employee gathers the necessary elements from storage lifts. This process is supported by a network storage system that ensures all required components are available when assembly begins. The assembly process follows a one-piece flow method, where an employee assembles each spindle step by step, ensuring precision at every stage. The assembled spindles undergo further checks for accuracy, with particular attention given to achieving perfect concentricity. Each spindle is measured and dynamically balanced to guarantee optimal performance. A QR code attached to the spindle's label links the component to its measurement data, ensuring traceability and quality assurance. The production of large combustion engines for both liquid and gaseous fuels at the Augsburg site has undergone significant advancements and changes. One notable achievement is the manufacturing of an 18-cylinder engine, which, when fully assembled, weighs over 90 tons. The production process begins with gathering data from design drawings and 3D models. This data is analyzed to determine the most efficient manufacturing processes. Tool data is then integrated into a comprehensive program that guides the CNC machines. Each NC program is meticulously simulated before being implemented on the machine. This step ensures that the machine operates smoothly and without conflicts, providing several key advantages. Increased confidence among programmers, greater precision in machining, reduced drive-in time, and significant cost savings are some of the primary benefits. The use of advanced simulation tools like Barrick has significantly reduced the drive-in time from 8 hours to just 2 hours, increasing workshop capacity and efficiency. Moreover, avoiding collisions and errors in the machining process prevents costly damages that could easily reach six-figure euro amounts. The 5-axis milling, turning machining center CP6000 exemplifies advanced manufacturing technology, combining both milling and turning capabilities into a single, powerful machine. This integration is referred to as combined processing and is pivotal for the efficient production of complex parts, such as microscope housings. The CP6000 is part of Heller's C-Series, renowned for its robust design, reliability, and precision. These centers are equipped with a fifth axis located in the tool, alongside a direct drive turning DDT rotary table. This configuration allows for flexible and powerful five-sided and simultaneous five-axis machining, as well as precise turning with positioned rotary axes. The spindle units feature swivel or tilting head kinematics, ensuring high torque and versatile performance across a variety of materials and parts. One of the significant advantages of the CP6000 is its ability to perform complete machining in one setup. This reduces the need for multiple clamping positions, thereby optimizing part costs and production efficiency. Tool management in the CP6000 is streamlined through the use of chain-type tool magazines, which can accommodate up to 150 tools. The tool holder's rigid, double-sided mounting ensures high dynamic performance, while the integrated tool provisioning station allows for swift tool changes, reducing downtime and maintaining continuous production. The pallet changer system further enhances efficiency with its hydraulic drive and robust design, ensuring precise and secure pallet positioning. This system supports high payloads and maintains accuracy through continuous alignment and surface blowout features. Standardized machine pallets with dim hole patterns facilitate quick mounting of clamping fixtures, further reducing setup times. Automation solutions are a key feature of the CP6000, with options for linear storage systems and standardized machine interfaces. These solutions enable continuous pallet feeding and optimal capacity utilization, making the CP6000 suitable for both high-mix, low-volume production and series production with small batch sizes. The machining process utilizes a variety of specialized tools to achieve specific tasks. The long overhanging tool with a disc cutter, measuring 125 mm in diameter and 16 mm in thickness, with a length of 195 mm, operates at a feed rate of 4,200 mm per minute. This tool is ideal for deep cutting and milling operations that require extended reach. For creating precise corners and pockets, the 40 mm corner mill is employed. An important tool is the boring bar designed for stepped boring. This tool, with diameters 52 mm and 117 mm, allows for the creation of stepped bores, which are essential in various engineering applications where different diameters are required within the same hole. Additionally, the process includes boring out to a larger diameter of 100 mm, which is critical for creating large, precise holes in the workpiece. While the solid carbide end mill, VHM shaft Fraser, with a 20 mm diameter offers high wear resistance and cutting performance for various milling tasks. The adapter plate with axis clamping, made from steel, 1.0503 or C45, securely holds and positions the workpiece on the machine table. To enhance precision and reduce setup time, automatic workpiece zero-point detection is employed, utilizing a wireless measuring probe to accurately determine the zero point of the workpiece. In terms of cutting and milling parameters, the face mill with an 80 mm diameter operates with a cutting depth of 3 mm and a cutting width of 75 mm, suitable for large surface area machining with consistent material removal rates. Additionally, the shank mill with a 25 mm diameter operates at a feed rate of 5,700 mm per minute, providing high-speed milling with an excellent surface finish. For achieving tight tolerances and fine surface finishes, semi-finishing and finishing tools are used. The semi-finishing boring bar with a 27.9 mm diameter and the finishing boring bar with a 28 mm diameter are specifically designed for these purposes. Automatic marking is another critical aspect, utilizing engraving tools for precise part marking and identification, ensuring traceability and quality control. Material-specific tools and operations are also integral to the process. The sprocket in the tool magazine, made from robust steel, 1.0980 or S420, is designed for heavy-duty applications and high durability. Precise hole drilling is achieved using the solid carbide spiral drill, VHM spiral bore, with a 9.4 mm diameter, known for its high penetration rates. Similarly, the housing for rotary introduction, made from steel, 1.7131 or 16 MNCRS5, ensures high strength and wear resistance for rotating components. The feed rate is set to 0.25 mm when using a corner mill with a diameter of 0.63 mm. This setting ensures controlled and accurate material removal. A shank mill with a diameter of 0.20 mm is utilized for general milling tasks, providing a balance between material removal rate and precision. For drilling operations, a solid carbide twist drill with a diameter of 0.29 mm is used, ensuring efficient and accurate hole creation. Direct thread tapping, utilizing a thread tap of size G34, ensures efficient and accurate threading operations. The moving column milling machines operate with a longitudinal movement of the column, which encompasses the head and tool. This movement is guided along its own longitudinal axis on a robust machine bed, allowing for versatile configurations for workpiece clamping. Key features of these milling machines include the independence of the workpiece clamps or tables from the machine bed and the column slide arm unit. This design enables the placement of parts in various shapes and sizes, resulting in different types of machines. The machines boast high precision in positioning and repeatability, facilitated by rolling guides for the movement of their axes and a compact configuration with a large-sized machine cast structure that ensures high system rigidity. The machines are robust and multifunctional in design. The machine base is heavily reinforced and calculated using finite element analysis. The slide, X-axis, moves along with the column, Y and Z-axis, over two linear rolling guides on the machine bed. Additionally, there is support with two roller shoes in the middle. Movement is achieved through a double gear rack system, master-slave configuration. These milling machines are particularly suitable for machining large parts due to the following: the ability to handle large lengths owing to the double gear rack system in the X direction, the capacity to machine large and/or heavy workpieces because the movements are independent of the workpiece positioning. User comfort and convenience are integral to the design. The machine offers easy accessibility, with the operator cabin either fixed to the column or capable of vertical movement to oversee machining. Control can be managed from the front through a dual control panel in the cabin and on the front of the machine. This is the Mirai's chassis and fuel cell system assembly line. After the frame is produced, the fuel cell stack is installed on it, along with the boost converter, hydrogen tank, and tubes. The fuel cell stack is the heart of the Mirai's powertrain, producing electricity from hydrogen and oxygen to power the electric motor. The boost converter regulates the voltage of the electricity produced by the fuel cell stack, while the hydrogen tank stores the hydrogen needed to produce electricity. Before the installation of the fuel cell stack and the hydrogen tank, a hydrogen leak test is performed using helium. This test ensures that the fuel cell system is free of leaks and can operate safely. After the fuel cell stack and the hydrogen tank are installed, the electric motor and the air compressor are prepared for installation. The air compressor is an essential component of the fuel cell system, providing the necessary air supply to the fuel cell stack. It is carefully integrated with the fuel cell stack to ensure optimal performance and efficiency. Next, the air compressor is married to the fuel cell stack. The motor is a permanent magnet synchronous motor that provides power to the vehicle's front wheels. It is designed to operate efficiently in conjunction with the fuel cell stack, providing a smooth and powerful driving experience. Following the installation of the motor and the air compressor, the drive shaft is installed. The drive shaft is a component of the drivetrain that transfers power from the motor to the front wheels. Finally, the front bumper and the wheels are installed to complete the chassis assembly. The front bumper is designed to protect the vehicle in the event of a collision, while the wheels provide traction and stability on the road. Before each Toyota Mirai body is brought to the former LFA Works assembly line, it is painted at the mass production line at Motomachi plant. The vehicle doors are then removed to enable more efficient interior work for Toyota's highly skilled craftspeople, as well as preventing doors from being damaged. This video also showcases wire harness, dash silencer, brake fluid tank, rear combination lamp, instrument panel, main battery, roof lining, and rear bumper installation. Spindle repair process. Spindles are essential tools for many industries, and regular maintenance is crucial to keep them in top condition, minimizing downtime and inefficiencies. However, spindles can degrade in performance or stop working altogether. Rapid resolution of spindle malfunctions is vital to maintain operational efficiency. Spindle rebuild services diagnose and address spindle failures, restoring machines to optimal performance. Here's a breakdown of the spindle repair process and how Setco can assist. Following the evaluation, technicians conduct thorough inspections of individual spindle components. Each part is assessed for wear, damage, improper fit, contamination, or other issues. This detailed inspection provides a comprehensive understanding of the spindle's overall condition, identifying additional problems that might affect performance. Technicians document their findings with photos and detailed notes, which are later reported to the spindle owner. Key components inspected include bearings, essential for movement and friction reduction. Technicians check for bearing failures that can impair spindle functionality. Bushings, reduce vibration and wear. Inspecting for wear or rust ensures smooth operation. Seals, prevent contamination of bearings. Technicians verify the effectiveness of seals to maintain spindle integrity. Part replacement and repair. After identifying the necessary repairs, technicians replace faulty or worn components with original equipment manufacturer (OEM) parts, restoring the spindle to optimal conditions. Part tests. Service specialists reassemble the spindle and test it to ensure peak performance. They balance the spindle and analyze speed and vibration, logging details for future reference. Each component is evaluated during trials to meet performance standards. If issues arise, previous steps are repeated to resolve them. Power skiving is a highly efficient and precise method for manufacturing gears, particularly suitable for large batch production. This versatile process is adept at handling both external and internal gearing tasks and is enhanced by integration with automation and other machining technologies. Integration with automation and other technologies. External automation for raw and finished parts. Automation plays a critical role in power skiving, especially for large batch production. Automated systems manage the loading of raw materials and unloading of finished gears, ensuring a smooth, efficient production flow. This reduces manual handling, minimizes errors, and increases overall productivity. Workpiece surface calibration and gear indexing. To maintain high quality and consistency, workpiece surface calibration and gear indexing are employed. Power skiving for external gearing. Roughing. The power skiving process begins with roughing, where significant amounts of material are removed quickly. This step sets the basic shape and dimensions of the gear, preparing it for subsequent refinement. Finishing. After roughing, the gear undergoes finishing. This phase involves precise machining to achieve the final gear profile, ensuring high accuracy and surface quality. The finishing process is crucial for meeting the tight tolerances required for high-performance gears. Deburring. Deburring is integrated into the power skiving process to remove any sharp edges or burrs that result from the roughing and finishing stages. This step is essential for improving the gear's functionality and lifespan by preventing premature wear and tear. Unloading. Once the gear is fully machined and deburred, it is automatically unloaded.